Nick here, M0NTV, and welcome back to my shack and to another video. And this one is going to be much more practically based, which I hope will be helpful to some folks who want to build a crystal ladder filter. Now, you may be wondering, those of you that follow my videos, why am I making another video about this? Because I've already got one I made a couple of years back now at least, called Crystal Filters for the Fearful. And that covered the design and construction of a particular design of crystal ladder filter called a Minimum Loss Cohn Filter. And the one that I'm going to do today is very similar to that, but it's got a little tweak on it, which is advantageous, which I'll tell you about. Now, these filters are different to the kind of classic Dishal filters, if I can call them that, to use the name of the software that many people use. Because to build a traditional filter, you would measure what they call the motional parameters of your crystal. You use a little test device, which I do use, and you'd measure the performance of this crystal on two different frequencies. You switch some capacitance in and out, and then that enables you to calculate some of the motional parameters. But it is quite involved, and then you have different levels of capacitance to offset all this stuff. The advantage with the cone filter, with the minimum loss filter, is that all you need is just one frequency measurement for each crystal, and then you group them together as best you can, and you get a group of crystals that are as closely matched as you can get them, and I'm going to go into all this. And then you use the same value of capacitance in the filter. So you might have, I don't know, 6 capacitors, but they're all the same value. And actually that value of capacitance controls the bandwidth of the filter. So it's quite cool, really. And all of the filters I've built myself are of this design, and you can get some pretty good results. Now, the only disadvantage with the cone filter really is that obviously to get steeper skirts on your filter, you need to add more poles, so more stages to it. But as you do that, you reach a point, particularly if you want a slightly wider filter, say for single sideband, where you start to get some more ripple in the passband. It's not so much of an issue if you're building for CW with a nice narrow filter, but the wider bandwidth you want, the more ripple you end up getting. And the only way to stop that is to reduce the stages, so that reduces the ripple, but then you don't get the steep skirts, so there's no such thing as a free lunch. So you have to kind of settle on what you can live with. Now, there's another adaptation of this minimum loss cone filter, which I've been interested in, and there's been a bit of buzz around some on Facebook and some of the ham radio groups about this just recently, although it's been around for some time. And it's called a QER filter, which stands for, here we are, quasi-equiripple crystal filter. Try saying that with your teeth in. Right? You can see why they call it the QER filter. And I'm going to show you my little hand-drawn schematic of what this looks like. So here it is. Now, if you compare this to the minimum loss cone filter, the standard one, it's very similar. The only difference is on the ends, on the input and the output stages, because on a standard minimum loss cone filter, you would have a capacitor, a series capacitor, and then you'd have the different stages then, the series crystal and the parallel capacitor, series crystal, parallel capacitor, etc., depending on how many stages, how many poles you've got in your filter. But what the QER filter does, it dispenses with these series capacitors on the end, and instead it doubles up the crystals. So this is actually a 6-pole QER filter, even though it actually uses 8 individual crystals, because on the input and the output they are doubled up, they're in parallel. And so what this means is it splits the signal. So technically, it kind of reduces the input and output impedance, apparently. You wouldn't think it when you look at mine in a minute. But what it does especially is it helps to flatten out the passband ripple. So even when you're building a larger bandwidth filter, then a wider bandwidth filter, then actually it smooths out the ripple, so you don't get the kind of ripple that you would get if you were building a standard minimum loss cone filter. So this is what attracted me to this. So the design has been around for ages, really. Dave Gordon-Smith, who has done an awful lot of work on measuring crystals. In fact, the little test jig you're going to see me using in a minute is his design. He wrote an article back in 2010, in the spring 2010 edition of the QRP Quarterly. I'll link to that in the Internet Archive so you can read that. And really, it was just a footnote, this design. He writes an article, very interesting article, and he just mentions this at the end. Ashraf Arhan uses it in the BitX, and Todd K7TFT of Mostly DIY RF. He sells his own ready-made boards, so you can build your own as well. So, and people have been building some of these recently and putting details up on Facebook. So I thought, yeah, I think it's time for me to try one of these. So that is what I'm going to be building. I'm going to be building mine for 10.7 megahertz, which is going to be the IF frequency. Just the last thing to say about mine is that at the moment I'm actually playing around with some FM demodulation, and which is kind of hard actually. Harder than I thought it would be. So I'm playing around with this. So I'm looking at some narrow band FM. Now, although it's called narrow band, it's still pretty wide compared to single sideband. So whilst, if I was building a crystal filter for a single sideband rig, I'd be happy to get a crystal filter that was maybe, 2.3 to 2.7 kilohertz wide. I need something much wider than that, probably something between, 9 and 13 kilohertz wide. So pretty wide. And if I was trying to do that with a regular cone filter, it would look like that wavy, choppy, terrible passband. So that's what attracted me to this particular design, because I'm pushing it to the limits, really. So, but if you're wanting to build one of these things for single sideband, if I can get it to work at those bandwidths, you should be fine if you're building a single sideband rig. So that's what we're going to do today. As always, I hope you enjoy, and I hope you get some useful stuff here that you can use yourself. So the setup here is, first of all, the homebrewed G3 QER Crystal Tester, which is essentially a little oscillator, and you'll see there's a space where you can pop the crystal in, just connected to the outer two holes. And there's a switch, because you switch capacitance in and out if you're measuring the motional parameters of the crystal. The good thing about the crystal filter that I'm building is we don't need to do that. All we need is a frequency reading, and that's why the output of the crystal tester is going to the Sanjian frequency counter. Ignore the graveyard of other projects behind. So Sanjian frequency counter, and you can see I've got this in I bought a little acrylic case for it, and just glued a couple of connections, one for the 12 volt DC power on that end, and then a BNC connector for the input. And that performs very well. Actually, it's pretty accurate. But in truth, it doesn't really need to be super accurate. It just needs to be consistent. So as long as it doesn't matter if it's out, as long as it's out for all the crystals that you measure, that's the most important thing. So that's drawing 173 milliamps. Most of that, the vast majority of that, is coming from the Sanjan frequency counter. I think the actual little test board only draws about 12 milliamps. So what am I doing then? Well, over here I've got a big pile of crystals, and what I'm going to do is, well, I'll show you exactly what I'm going to do. So I'm going to reach over to my pile of crystals and grab one at random here, and I'm going to put it in to the G3UUR tester and take a reading. So what we got here, 10.697844, let's call it. And so over here to my Mac, we've got a spreadsheet here, so I'm just going to put that in, 10.697.844, and that's number 37 now. So all I'll do then is I'll come down to here, grabbing the crystal with one hand, excuse me, and make sure 37 is going to go down here. Now this is great until I have to move them. So every one of these crystals is numbered, and that is corresponding to the actual values here, and it will just mean that I can see all the values on the screen at the same time, and then I can match 6 or however many I need that are closest in frequency together. So a progress report of the 100 crystals that I purchased them from AliExpress. I think I never buy less than 100 for reasons that will become clear. So I've gone to categorise them all. I had to end up sellotaping them down to this bit of paper. It was such a great idea. If I had a little container that had 100 different gaps in that I could label, that would be a better idea, wouldn't it? But anyway, it works, so they don't all move around. 5 of them were completely useless. So 2 were totally dead, absolutely nothing at all. And 3 were just random frequencies jumping around all over the place, so were unusable. So that's 5% wastage, which is not bad really, because they're not very expensive at all. And so you'll see there are some gaps here. That's because I've selected some for my actual filter, and so I will show you what that looks like now and some of the calculations that I've done on screen. So here is my completed spreadsheet from 1 to 100. Here's the 5 dead ones down here. I had to take the decimal places out here because the spreadsheet software didn't like it. So these are all frequency measurements in hertz. And so that was all of them. Great. So I now know what the resonant frequency of each of those crystals is. So what I then did on a different tab is I got the software to order them. So what I've got here then now is the frequency of each crystal listed in order. So we're going from the highest frequency here, which is 10.698381, down to the lowest one, which is 10.697794. And then I just did a very simple little formula here on this difference column. Now what this does is it calculates the difference in frequency between this crystal and the one immediately above it. Okay, so that's why this is 0, because there's nothing immediately above it, and you can see the 68 hertz difference between this one and this one. And that just makes it easier immediately when you're looking at it to see how closely matched some of these are. And for my purposes, for the crystal filter that I'm going to build, I need 8. So I need 8 crystals as closely matched as I can get them. So I was just looking down here and I settled on this group down here, which I've highlighted in red, which starts at 10.698194 going down to 182. So you can see that's only a difference of 12 hertz across all 8 crystals, which is, I mean, superb. Now, in reality, you can't take these readings too seriously. They're not that accurate because of the Sanjan frequency counter, because of the temperature of each crystal. Every time you pick them up and hold them in your hand, you're changing things. The current running through the circuit that I tested them with, all these things will have an effect. But given that essentially I treated all of these crystals in the same way, that's it's a pretty good indication. So they're as closely matched as I'm ever going to get them. So I've settled on those 8 crystals that are going to go into my filter. Well, welcome to the bench. And here is my schematic for my QER crystal filter. And you see I've gone for a 6-pole. And although it's 6 poles, it's actually 8 crystals, because the ones at the 2 at the beginning and the 2 at the end are in parallel. So yeah, so that's what I've gone for. Now, what I then did was create my board. And so here's my little copper clad board. Now, all the usual rules apply. So before I used this, I went over it with some fine wire wool, remove any lacquer that might be on it. Then went over it with the multimeter, make sure that it's nice and conductive over the whole surface. I sawed it in half, as you can see, roughly. And then went about actually designing what this was going to look like. And to be honest, I didn't write this down because I've done so many of these. I just did it as I went along. So these 2 at the end here are for my SMA connectors. And then I calculated the rest. I could get all the rest onto this board with a little clever bit of jiggery pokery there. I coloured them in this occasion so I could just see exactly which bit was going where, to make it easier when I was going over with the Dremel, or cheap equivalent thereof. Other brands are available. And I marked it out with some of those old pens you used to use for writing on CDs. Remember them? So quite handy. So the board, and then of course I've been over it again now with the multimeter, just test that all these little isolated conductive pads are indeed isolated from one another and from the ground plane, and they are, which is great. So now what I'm going to do is populate the board, and then I'll show you what it looks like. And here it is. So let me just come in a bit closer here so you can see what it looks like. There we go. Now you see what I mean about fitting all those crystals in there. It was a bit tight, but it seems to have worked, and experience has taught me to allow plenty of room for these capacitors here, because there may be plenty of swapping of capacitors, taking these out, adding other ones on, because it's the capacitance in these cone-based minimum loss filters that determines the bandwidth. And so there's usually a fair bit of desoldering, resoldering capacitors, so you need enough space to work with. And some of the first ones I built here, it was just too hard to get in and do it. So so I've allowed plenty of room for that. You'll notice these little connections here and up here. This is where I will be having some impedance matching device, either a transformer or an L match network, something that will match to the impedance of the actual filter itself, to 50 ohms. but I haven't decided on what I'm going to do with that yet. So, but I've left space again. Experience tells you to leave some space for it, because usually you do it and connect the SMA right into here, and then you're in all kinds of trouble because you've got to fit in transformers and there's no space and all the rest of it. So anyway, it's come together pretty well. So I guess the next thing to do now is to get it inside and to have a look at what it looks like. So just a little status report. This is the board now. Now, full disclosure, I've completely replaced the capacitors twice at least, because the first time I put on 270 picofarads, which gave me an incredible filter, but it was so narrow. I mean, it was too narrow even for CW. It was really, really narrow. And I'd forgotten the fact with Cohn filters that the higher the level of capacitance, the narrower the filter. And usually I'm building SSB filters and I want a fairly narrow filter. But this time I'm not. This time I'm actually building a crystal filter for FM, for narrowband FM. And it may be narrowband, but it's still a lot wider than single sideband. So instead of aiming for a filter with a bandwidth of, say, I don't know, 2.4 to 2.7 kilohertz, I'm looking here to do something really between, well, anything between 9 and 13, I suppose. So a lot wider. So I needed something wider. So I needed to go the other way. I need to go down. So I stripped out those 270 picofarad caps and stuck in some 10 picofarad caps. And I did the exercise I'm just about to show you now. Worked out what the input and output impedance was. Built a simple little L match on the input and on the output. And it worked really well, but it was just still a little bit too narrow for my purposes. So I've started again. So now I've got 6.8 picofarad caps in. And you see what I've got here. Well, hopefully you can just about see what I've got here. I've actually, this is actually a trim pot, a little tiny potentiometer, and it's also got another resistor in series with it. And you'll see that this leg is not connected, so I'm just using it as a variable resistor. So that's a 150 ohm resistor, and this is a 1k ohm trim pot, and it's the same on the other end. And basically what you do is you adjust the resistance until you get the flattest passband when you connect it to something like a NanoVNA, and that's what I have done, and I can show you that here. So now look at that, that's really good, but that is with everything maxed out. So on here, I kept having to increase the size of the resistances up and up and up, because usually when I built a regular Cohn filter, you know, it's had like 100, 200 ohms impedance at the most. This has bust beyond 1k now, and I think it's close on to 1.2k ohms impedance. And I'm sure that's something to do with the fact that I've got this paralleled crystal on the input and the output, and that seems to have really affected that, but in a good way, because, you know, look at that. Now you will notice, if I can balance this down, I'm not sure I can very easily, but just to show you clearly, the insertion loss is horrific, but of course it's going to be, because you're dropping over 1,000 ohms worth of resistance of your signal. So, but that's not going to bother us, because we will be swapping out all that convoluted resistance network at the beginning and replacing it with a so-called lossless impedance matching system. And I think this time I'll probably go for a good old tried and trusted conventional transformer. And I think I'm going to shoot for about 1,200 ohms, I think, to 50 ohms, and produce something for that. And hopefully then that will give me a wider filter, which this is, with a good input and output impedance. Now, I thought I ought to just mention in a bit more detail how I'm doing this calculation, because sometimes people ask me about this. So effectively what you need to imagine is that our source, which is the NanoVNA in our case, is putting out a signal with 50 ohms characteristic impedance. And that's going into our load, which is our crystal filter. And we don't know what the impedance of our crystal filter is. And I'm using the word impedance, but really I'm just talking about a pure resistance. So you just have to bear that in mind over the next couple of minutes. So how do we find it out? Well, what we do is we insert a series resistance. Now, what I need you to imagine is that this resistance that we've put in, and it's going to be a variable resistance, is really part of this. It's really part of the source's characteristic impedance. Even though we've put it in here, you need to kind of imagine this resistance being together with this one. And this is going to help us calculate what this is. So how do we do it? Well, what we do is we adjust this resistance until we get the flattest passband. And so you just keep increasing it until it gets better and better. And you'll see when you've got an optimally flat passband. And so once you've got that point and you're happy with the shape of the passband, then you disconnect the NanoVNA and you measure what this additional resistance is that you've put in. And so in my case, it was about 1,150 ohms. And so what you then do is you sum together, you add this source resistance, 50 ohms, and this additional resistance that you've put in, 1,150, and that will then give us our filter impedance or filter resistance, which is 1,200. And I didn't mention in the previous video about adding in the 50, and that's important because you need that, because essentially what's happening is when you're seeing the flattest passband, you're seeing the two impedances being matched. And when I say two impedances, I mean this one and this one counts as one, and this counts as the other. Now we know this portion of this impedance because it's the NanoVNA, it's 50 ohms. But once we've measured this one, then we know what the total is here, and we know that this total matches this. So although we didn't know what this one was, we do now, right? Because we add these two together, and this is the simple voltage divider method. And it works pretty well. And, you know, major respect to Charlie Morris, ZL2 CTM. He's the one that I picked this up from first of all. And I've used this on all my crystal filters, and it seems to work really well. And here is the finished filter, and you'll see now I've got the addition of these impedance matching transformers at the input and output, and I think it's bi-directional, it doesn't matter which one's the input or the output. So what I did is I settled on an impedance of about 1,200 ohms. And what I soon discovered is that as you increase the bandwidth of this filter, not only do you need to decrease the value of the capacitance, which I'm down to about as low as you're going to get really, I mean 6.8 picofarads these are, and obviously there's not much more room to maneuver there, so I'm pretty soon you'll be maxing out what the actual practical bandwidth of this thing will do. But anyway, so 6.8 there. So as you increase in bandwidth, you decrease the capacitance, but also you increase the input impedance. So if you've got a much narrower filter, you'll find the input impedance is much lower. And and that can be useful if you're building a sideband filter, or certainly if you're building a CW filter, much more forgiving. I've got 1,200. I've got to match it to 50 ohms. So I'm not going to go into all the details of this now. I will just give you the figures. If you're interested in how I build these things, then please have a look at my recent 2 videos on building transformers on conventional ones like this and on transmission line transformers. But for the purposes of this, I have an impedance ratio of 1200 to 50, so that's an impedance matching ratio of 24. Now, to find out the turns ratio, you have to take the square root of that. So the square root of 24 is, well, 4.8989, etc. So let's call it 4.9. Now, I know that in order to get the required performance on the primary here, I need to see 4 or 5 times the impedance hanging off it. So I need to be seeing 200, 250 ohms inductive reactance at least on the 50 ohms end. And at 10.7 megahertz, that means I need at least 3 turns. So I went one more than that. So if I put 4 turns on the primary, that would mean 4 turns times the impedance matching ratio, which is 4.9, would give me 19.6. Well, of course, I can't have 19.6 turns, but let's call it 20. So that's what I went for. I went for 20 turns on the secondary and 4 turns on the primary, and these are FT3743 ferrite cores. And, well, you'll see for yourself how well that performs. And so you see I've connected my filter now to the NanoVNA, and have a look at that. So you can see that's pretty good. You look at the insertion loss, marker 1 at the top there, minus 2.64. So that's great. And they reckon that, you know, anything between 2 and 4 dB on these things is acceptable. Obviously, the lower you can get it, the better. But it's pretty flat. There's a bit of a bump down there, but that's not bad. And it's pretty similar to what I saw when I just got the resistive termination on the inputs and outputs. So it's, yeah, so the transformers are obviously doing their job. And it's a pretty good looking filter, particularly on the right hand side. You can see that's some attenuation and a nice steep skirt on that end. So I think that should serve me well. So here are some results, and this is using the NanoVNA Saver software, and you'll see I've taken a wider sweep of frequencies here, so you can see how the filter's performing over a wider bandwidth. And yeah, you can see it's pretty good. I mean, as I said, very impressive on the right hand side, but pretty good here as well. The SWR is not bad. The leading edge is not so good, but the tailing edge, these are approximately the red marker and the green marker, the minus 3 dB points. But for most of the bandwidth of the filter, the SWR is pretty good, and you can see that reflected down here on the parallel impedance, and the highest that gets to is, well, about 75 ohms or something, but that's only like, 1.5 to 1 SWR, so that's not bad at all. It's interesting to see here, this is the group delay, this is the ringing of the filter, which again, there's not too much you can do about that, particularly when you're building your own, but it's just interesting to see. It's where how quickly the filter will kind of settle down after it receives a signal. But yeah, so that's what it looks like there. Pretty good. I'm quite pleased with that. I want to just show you a couple of screen grabs now that I took with my spectrum analyzer, so you can actually see the bandwidth in a bit more detail. So here is the first slide I would like to show you, just to point out that the tracking generator was set to minus 20 dBm. It's not that I've suddenly got an extra 20 dB of loss, which would not be good. So, but it is measuring, if you take 20 off that, a slight bit more of insertion loss than the NanoVNA did, but not a great deal. So you can see that, so that works pretty well, and that gives me a minus 3 dB bandwidth of 8.8 kilohertz, which is great. So, you know, almost 9, which is fine. That was the kind of minimum I wanted. But what I find helpful when I'm analysing crystal filters is to also consider the 6 dB bandwidth. So in other words, this 8.8 kilohertz, the minus 3 dB bandwidth is you know, the where the signal is at half the strength compared to here. We're going to look at where the signal is at a quarter of the strength compared to this point, which is here. And so that's very good. So 9.92 kilohertz, so nearly 10. So this should be ideal, really, for my purposes of narrow band FM. So there we go. And as I said, I think probably the high impedance that I was finding is probably more because of the wide bandwidth that I was shooting for. And you may well find, if you're going to build one of these things for a narrower bandwidth, that your impedance will be much lower. And hopefully it will perform at least as well, if not better, than the one that I built. Thank you very much for watching this video and for supporting the channel. If you've enjoyed it, please remember to like and subscribe, and you can keep in touch then with some of my other home brewing projects. I will see you on the next video, but until then, thanks very much. Look after yourself. Bye-bye. 73.